All right, students, we're going to learn about Newton's third law. This is in your notes on page 5. Please get out your notes and get to page 5, which is related to Newton's third law. We've already learned about Newton's second law and first law, and today we're going to learn about Newton's third law. All right, starting on at the bottom of page 5 of my notes, every force, produces an equal and opposite reaction force of the same type. Every single force in the universe has an equal and opposite third law pair. That's kind of hard to put our head around, but some we can see and some are harder to see. These forces are equal in magnitude and they are opposite in direction. Okay, for example, the first object exerts a force on the second object, which will cause the second object to exert the same force back. So for example, if I push on a table by 10 newtons, the table is going to push back on me for 10 newtons. You've heard this before. For every action, there is an equal and opposite reaction. Okay. Now over here to the right, I have two objects, objects 1 and 2. So I'm going to read the next sentence, and I want you to think about these two objects that are sitting on the table. They're touching one another. One is, let's say, putting a force on number 2. So if object 1 and object 2 interact, the force exerted by object 1 on object 2 will be equal in magnitude, but opposite in direction to the force exerted by object 2 on object 1. So let's look at that drawing I have, and let's actually see what I'm talking about. So let's pretend that force over here, this object 1 is pushing on object 2 and is going to put a force by 1 on 2. So that's maybe the notation that you'd like to use. You're going to need to keep track of how you're going to do this. So I go force by 1 on 2. So it's a 1, 2. And what that says, therefore, is that there will be an equal and opposite force by 2 on 1. So the lengths of those vectors are the same, but they are in opposite directions. So technically, the force of object 1 in magnitude is equal to the force of 2 on 1. The absolute value brackets will take care of the magnitude. So if one of them is negative, one of them is positive, that statement is true because the negative becomes positive, the absolute value of that. Now, how do I draw free body diagrams and identify third law pairs? So I'll start with the force acting on object 2, which is right here. So we will add all the forces acting on object 2. So we have from object 1 a force acting on it. So there's the force from 1 on 2. And we have force normal from the table. And we have force of gravity that's acting on object 2. And then on object 1, we will have force from 2 by 1. I'm sorry, force by 2 acting on 1. We'll have force normal from the table. And then we have force of gravity acting on what? On object 1. And what I just stated, I should probably make this a little bit smaller so that they're identical in length. There we go. Force from 1 on 2. We have two pairs here. They are equal in magnitude and opposite in direction. That right there are third law pairs. Okay, notice that it requires two free body diagrams to identify third law pairs. In other words, it is two objects. You cannot have a third law pair acting on the same object. For example, force normal and force of gravity. Yes, they're equal in magnitude. Yes, they're opposite in direction. They are not third law pairs. They are only on one object, and there must be a second object involved. We will discuss in a little bit later what a third law pair is for force normal and what the third law pair is for force of gravity. Okay, again, must have two objects to have third law pairs. How about this? I'm pulling on a rope. Here's the rope. Here it's attached to a wall. I'm going to pull on the rope. There's the force of me pulling, and let's say I pull by 20 newtons. What's the rope going to do? The rope is going to pull on me by how much? This is the pull of the rope on me. Guess what that's going to equal? 20 newtons. That's the rope on me and me on the rope. Two objects involved. Next object. Let's take a burning fuel in a rocket, which causes exhaust gases to escape from the backside of the rocket. So we're shoving gas out the back end of the rocket. That gas will bombard all the air particles, okay, putting force on the air particles. The air particles then will push back on the rocket and in an equal but opposite direction, okay? So this thrust is what they're calling. Thrust is actually the force on the rocket by the air. This force is the force of the rocket gases, we'll say. Gases, excuse me. Force from the gases on the air. Okay, so if I wanted to draw a free body diagram, I could say, okay, this is the force from the air particles on the rocket. That's the thrust. And what do I say? Newton's third law? Well, this is the force of the rocket gases on the air. And that is the third law of pairs. Okay? They are equal in magnitude, opposite direction. How about a plane? We got the wings of a plane. They're angled. That's considered the angle of attack. The air, which is highlighted in blue here, comes along and hits that angled wing and gets shoved downward. Okay? So the plane, the bottom of the plane is putting a force on the air. So the bottom of the plane is putting force on the air. This is the plane on the air. And Newton's third law says, the air, the force of the air on the plane. And therefore we have liftoff. These are third law pairs. Notice there are two different objects involved. Third law pairs. Okay, yes, there's other forces. I'm only trying to talk about the ones that are third law. All right, how about a bug? Bug hits the windshield of a car. Okay, so you can imagine, visualize that. You're driving down the road on 99, bug hits it, splat. And so we got a force from the bug on the car. We got a force from the car on the bug. Ask yourself, which force is greater? Even though I've told you, third law, some of you are going to say that the force of the car on the bug is greater. And I just got finished saying, third law, it is a physics law, period, law, not like a principle, it's a law. That the force that the bug, here's a free body diagram of the car, force of the bug on car will be equal and opposite, here's a free body diagram of the bug, of the force of the car on the bug. There is a difference between the bug and the car. The bug and the car have different masses. So sum of the forces equals ma. If the forces are the same, but the masses are different, then the acceleration will be different. So for example, the force on the car by the bug, say it's a small number, the mass of the car is huge. A small number divided by a huge number means I'm going to have a really teeny acceleration that was created by that force because the mass of the car is substantial. However, that same force then gets divided by the little teeny tiny mass of the bug. That's the acceleration that the bug is going to experience is substantial. because of the fact that it's small mass. So there's where the size of the car and the bug comes into play. It's not the force that has the impact on the change in motion. It's the mass, okay? But again, the forces are the same. They are equal in magnitude, and hopefully you can see they are opposite in direction. So I'm going to say that the force of the car on the bug is equal to the force of the bug on the car. Those absolute value brackets mean that the magnitude. So one's negative, one's positive. You say left is negative, then the force of the car and the bug is negative, and that but again, the absolute value. So the magnitudes are identical and the directions are opposite. So let's just review a couple things. This was all the key points related to first, second, and third law, which we are now done learning about, not done using them, that's for sure. Velocity is constant. We know that acceleration is 0. You learned that in unit 1. You learned that because acceleration by definition is change in velocity over change in time. If velocity is constant, that numerator is 0, and 0 divided by any number is 0. Okay, we have a new thing that you've learned. This is first law, by the way. If acceleration is 0, then by definition, I can't have a net force. All the forces added up must equal 0 because of first law. If there's no net force, the state of motion will stay the same. Now, just because an object has constant velocity does not mean there must be a force in the direction of its motion. I'll give you an example. Here's a hockey puck on ice. In other words, it's frictionless. It's traveling with a velocity of 1 meter per second. And its acceleration is 0. In other words, the velocity is constant. If I drew a free body diagram, this is, let's say the velocity is to the right. I have force normal and force of gravity acting on the hockey puck. Whoops, that's force normal. A lot of people will try to tell me there's a force to the right and it's a force applied, and that is not the case. There's nobody's hand, there's no stick. So once again, just because it's traveling with a constant velocity does not mean there's a force applied on it. Okay. Next thing, we haven't talked about this yet. We're going to get into systems much more detail. When considering an object or a system of objects, we're only interested in the external forces. Here's a picture of two people standing on a cart, and if they are standing there pulling on each other, we got some internal forces going on, but that won't accelerate the cart because those forces are internal. All right, next point. Second law is one of the most powerful relationships in physics. The sum of the forces is equal to mass times acceleration. I can sum the forces in the x. I can sum the forces in the y. I could sum the forces in the third dimension, which you have not done, which is z. But don't forget, if you determine the acceleration in the x direction is positive, then the net force in the x direction must be positive. If you determine the acceleration in the y direction is negative, then the net force in the y direction will be negative, okay? If you find that the object has an acceleration at 53 degrees above the horizontal, then the net force will be in the 53 degrees in the horizontal. The direction of acceleration has to be in the direction of the net force. Lastly, third law is one of that you students commonly misunderstand. Third law pairs, action and reaction forces, must act on two different objects. Identify, for example, the third law pairs for a book sitting on a table. Here is a book. Here is a table. If I draw a free body diagram on the book, that's the force normal. That is the table on the book. Force of gravity, that is the earth on the book. Okay. Don't tell me force normal and force of gravity are the third law pairs. That's only one object. It's only one free body diagram. So how about we draw a free body diagram for the table? This is the book. This is the table. The table has to be on the floor. So I have force normal. This is the floor on the table. I have force of gravity on the table, which is the earth. on the table, right? That's pretty small. I hope you can see that. That is the Earth on the table. Okay. So there's two objects. What are equal and opposite? Oh, I forgot one force. I don't see the third law pair. Okay, that's not the only forces acting on the table. The force normal from the floor, the force of gravity on the table from the earth, but isn't the book also pushing down on the table? Oh, no, don't do that. Isn't the book also pushing down on the table? This is the force that's being applied by the book on the table. Okay. And there's my third law pairs. Okay. That force by the book on the table, since the force normal on the book is equal to the weight of the book, right? Isn't this equal to the weight of the book? And those two forces are equal to one another. That's going to equal the weight of the book. Okay, so the weight of the book is pushing down on the table. The table's pushing up on the book by the same magnitude. Okay, there you go. Where's the free? Let me ask you this question. Go back. Okay, it's way up, but I don't want to get. No, it's not. It's right here. Excuse me. Every force, not one force, every force produces an equal and opposite reaction force. Now go back. Where is the third law pair for the force of gravity? Anyone? Can't see. Here's the center of Earth. The table is pulling up by the same magnitude. That is the table on the Earth. So that's the third law pair with that one. And guess what? I'll do it in green. Well, I'll circle it in green. Let's make a bigger dot. The book is putting a force of gravity on the Earth. You haven't learned about that. That's called Newton's universal law of gravitation. That's the big G. We actually talked about it, I think. Big G, M1, M2. Every object puts a force, an attractive gravitational force on every other object. So, okay, hope I didn't confuse you. Now, we're going to go to some problems where we're going to use the third law pairs and actually practice the problem. So take your notes and turn to page 9, and let's practice using third law to solve some problems. All right, I'll read this while you guys get to that page. I have a man of mass, capital M equals 75 kilograms, and a woman of mass, lowercase m equals 55 kilograms, standing facing each other on an ice rink, wearing ice skates. In other words, a frictionless surface. The woman pushes the man with the horizontal force of 85 newtons in the positive x direction. So here's the force of 85 newtons of the woman on the man. I've already drawn it to save some time. What is the man's acceleration? Acceleration equals question mark of the man. Okay, now over here to the left, I have highlighted in green. This is actually very common on the AP exam. So listen, capital M and lowercase m are used to distinguish between two masses on the AP exam. I cannot stand capital M and little m. Is it easy to get capital M and little m mixed up when you are doing a whole bunch of math? Yes, it is. Now, just like Expert TA, you are required to use the same exact variable designation that the problem gives you. However, if you choose to change the variable and provide a little notation, like I have done here in green, of something different, as long as you have defined it, you may use something different. I don't like capital M and then little m. So I want to use M1 and M2. So I am going to call the woman object 1 and the man object 2. Therefore, I can get rid of these awful notations they've given me and say M1 and M2. Okay. All right, we've got to figure out the man's acceleration. And so in order to do that, I'm going to have to draw a free body diagram on the man. There's the force normal upwards. There's the force of gravity acting on the man, which is object 2, which is equal to the mass of the object 2 times the gravitational acceleration on Earth, which is also equal to the weight of object 2. Okay. I have one force acting on object 2 because it's frictionless, and that is the force of 85 newtons. I only have one force, so I can solve that. I can sum the forces in the x direction as mass times acceleration in the x direction. It's a positive 85 newtons because it's to the right. Oh, I left off my little symbol, which I defined as M2. What mass? I'm summing the forces equals mass. Which mass? Well, this is the man, so mass 2. So I'm going to divide 85 newtons by mass 2, which was 75 kilograms, which will be equal to the acceleration. And we'll find that the acceleration of the man is a positive, where am I? 1.13 meters per second. And that makes sense. Sorry, meters per second squared. This is the answer to A. I will call this positive, which I didn't have written up here, but at any rate, it makes sense that he's going to travel to the right with an accelerator, or that he's going to accelerate to the right. B. Now, I got to have a free body diagram on the woman. I have force normal up. I have force of gravity acting on object 1, which is mass 1 times g. That's also equal to the weight of object 1. Okay. Well, what force do I have acting on her? Well, the man is putting a force acting on her, which is equal in magnitude, opposite in direction. So we'll actually call this is force 1 by object 1 on 2. This is force of 2 by object 2 on 1, which is 85 newtons. And notice it's to the left, which is now in the negative direction. If I want to know, you would not have been able to solve this problem if you did not have an understanding of Newton's third law. If you did not know that this magnitude of force is equal but opposite direction of the force that the man puts back on the woman, you would not be able to solve this. So I'm now going to sum the forces on the woman. So this is, again, the forces acting on the woman in the x direction. I will equal the mass times acceleration. What mass? Well, that's the mass of the woman, and that is her acceleration. And there's only one force acting on the woman, and it's to the left, so I better keep that to be negative. And then that will equal the mass of the woman times acceleration. And so I will find the acceleration of the woman to be negative 85 newtons divided by a positive mass. Mass cannot be negative, it is a scalar. And then I will find her acceleration to be negative 1.55 meters per second squared. Does it make sense that the acceleration of the woman is to the left? That's what that negative means. Yes, it does. Now here's some, that's answer to B, excuse me. Here's something that you should notice. The acceleration of the woman is larger than the acceleration of the man. So two things. One, it makes sense that the acceleration of the woman came out negative because we said to the left is negative and she's going to accelerate to the left. It also makes sense that her acceleration is larger than the man's. It makes sense to me. Why? Well, her mass is smaller. So the forces are equal, but the mass of the woman is smaller. And that's why she has a larger acceleration. I'll go back to the situation with the bug and the car. Everybody wants to tell me that the car is going to put a larger force on the bug. That is not true. Newton's third law clearly states that the force by the bug on the car will equal the force of the car on the bug. Now, because the mass of the bug is so much smaller, that force, it will create a much larger acceleration on the bug than the acceleration on the car. And that's where the masses come into play. All right, I'm going to let you answer these two questions on your own. You hopefully will get them and I'll see how you do. Okay, this one right here, I'll do, I'll help you get started, and then at the end, maybe I'll let you identify your third law pairs by circling them. And then when I come back, we'll go over your answers. We have a situation where object B sits on object A, which is sitting on a table. We have been asked to draw free body diagrams of the forces acting on block B, acting on block A, and the table, and then circle and identify third law pairs. Now, it can get tricky on how you use your nomenclature as far as your system of, let's see, of how you want to draw your forces, and I'll kind of hopefully be consistent, not always consistent. This is a free body diagram on B, okay? Free body diagram on B. The dot represents the center of mass at B. The forces acting on B. Well, I've got the force of gravity acting on B, which is equal to, just for chagrins, the mass of B times little g, which is also equal to the weight of B, okay? I've got the force normal. What is the force normal being, where is it coming from? Well, it is from A on B. Okay, from A on B. Okay, now free body, any other forces? No, that's it. Free body diagram on A. This is the center of mass of A. Okay, so here's the dot. Now let's draw the forces acting on A. I'm actually going to have to make this dot a little bit bigger, and that's okay. All right, dot doesn't have to be perfectly circular. All right, I've got the Earth acting on A. Force of gravity acting on A, which equals the mass of A times little g, which is also equal to the weight of A. All right. I have a force normal upwards. Which one is that? Well, that's the table acting on A, is it not? Okay. What else do I have acting on it? Well, B is on top of A, so B better be putting a force on A. So sure enough, I have a force from B on A. Okay. Next, free body diagram of the table. Any other forces acting on A? No, if nothing else is in touch with the table or scar A. B's not touching A. Table's touching A. That's 2. And then I got the field force from the gravity, and that's 3. That's the only 3. They're not moving. There's no friction. We're not trying to move it. All right. I made a bigger dot for A table. I actually don't need any bigger dot. I just need approximately the same size dot. All right. There's the table. Well, I'm going to do the easy one. This is the force of gravity acting on the table, call it T. That is the mass of the table times little g, which is equal to the weight of the table. Okay. All right. The force, the table has legs. Here's the floor. So we have a force normal from the floor on the table. Okay. Now, is A touching the table? Yes, it is. So that is the force of A on the table. Okay. Now, let's draw the center of the Earth. And this one I got to do big. It wasn't in the instructions. This is the center of Earth. All right, there's the center of Earth right there. Isn't the book or block B putting a force upward? This is force of gravity on the Earth by B. Isn't the excuse me, let me just go. This is more than what the instructions said, but I'm just going to do it anyway. This is the force of gravity by B on the Earth. This is the force of gravity by A on the Earth. This is the force of gravity by the table on the Earth. Now, if I wanted to create and circle free third law pairs, I'll do one for you. You do the rest. This is the force on A by B. This is the force of B on A. These are third law pairs. Notice they're from 2 different free body diagrams because they are on 2 objects. Those are equal in magnitude, opposite in direction. Okay, you circle the rest. Let me see how many pairs I can come up with here. 1, 2, 3, 4, 5. Based on how many free body diagrams I have, I can come up with 5 pairs. Let me count again. 1, 2, 3, 4, 5. Yep, I can come up with 5 pairs. Can you come up with 5 pairs? Good luck. We'll review when I get back.